On this video, we're going to look at different types of radiation. So, you've got alpha, beta, and gamma as the main types of radiation we're going to look through. I know there are various other ones, but these are the ones that involve the nucleus, and that's why they're called nuclear radiation.
Alright, so we've got alpha radiation, which has 2 protons and 2 neutrons. Now, it's not really a surprise, it comes from the nucleus. Protons and neutrons come from the nucleus, and so we have 2 protons and 2 neutrons coming out. Now, each proton has a charge of 1 plus, or plus 1. And because you have 2 of them coming out, then that means you have a charge of 2 plus, because obviously you have 2 of them plus 1 each. Double that, you get 2. Now, what's really important is it's written here, the structure actually changes because of the nucleus releasing 4 nucleons. Now, if you lose 2 protons, then obviously the elements are dependent on the number of protons, and so when it says the structure changes, it actually changes it from one element to another. So if you have a look down here, where it says the original isotope loses 2 protons and 2 neutrons, there's an equation looking thing here. This is called a nuclear equation. And we use nuclear equations to show how one element changes from one thing to another based on what's happening to it. So in this particular case, we have an alpha particle being released. Now, we originally started with a mass of 238. We're losing 2 protons and 2 neutrons. So if you lose 2 protons and 2 neutrons, that gives us a mass of 4 that we're losing, and a charge of 2 that we're losing. Now, because we're losing a mass of 4, 238 goes to 234. That's why from uranium it goes to thorium. If you have a charge of 2 that we're losing, so instead of 92, we'll go down to 90. So that's why we get to thorium. Now, when you are first doing this, what you should always do is you should always figure out the mass number first, and then you should always figure out the atomic number first, not the mass number. That's really important. Do the atomic number first, because if you do the atomic number first, that tells you which element you have. So I'll go through this in a little bit more detail later, but make sure you go and do the atomic number first. Alright, so there are various ways that this can be written for alpha particle. You can see down on the bottom. The video is kind of in the way. Hang on. I'll temporarily remove my face. So on the bottom here, uranium-238 is unstable. After it changes to thorium, you can see an alpha particle is being ejected. So beta is the next type. We have 2 different types. We have a beta positive and a beta minus. These represent the charges of the beta particle itself. Now, beta minus is an electron from the nucleus. But beta positive is a positron. But hang on, did I just say electron coming from the nucleus? Yes, you heard that right. Now, it's called beta minus because it has a negative charge. The reason why this happens is because we have a neutron decaying into a proton and an electron. So what that looks like is this. You have a neutron. Neutron has a mass of 1 and a charge of 0. It decays into a proton. Proton has a mass of 1 and a charge of 1. Now, in order for that to be balanced, we need an electron there, which has a charge of -1 and a mass of 0. That way, when you add the 2 together, it goes back to the original. No energy is lost that way. However, because a subatomic particle change, or any particle change, whenever something gets destroyed, particle-wise, so in this case a neutron gets destroyed, it always releases something else. In this particular case, it is called an antineutrino. Now, whenever something is decaying, remember the point of a radioactive isotope is it wants to decay energy to balance itself out, because it's got too much excess energy. We'll talk about this a little bit more later, but basically, if you have too many neutrons put together in a space, or nucleons put together in a space, it stores up a lot of energy. Imagine there's like a whole bunch of you guys in the room, and you guys are all stored up into this really small space. Well, if you guys have that issue, then obviously you guys all get really energetic, you guys all get really uncomfortable, and that's why you want to kind of break out. You can imagine it like that. Alright, so with beta positive, we have a similar effect, however it applies for a proton. So, one proton, mass of 1, charge of 1, that changes into a neutron this time. And then we have a positron. Now we still use the E, and to indicate which one we have, we normally either do a plus or minus. This time, we get a neutrino because we gained a neutron. I know it's a little bit weird. We gained a neutron, and then, sorry, we gained a neutrino. The other one, we gained an antineutrino to balance out the fact that we lost a neutron. And then we also release energy. So, what types of isotopes actually have this effect? Carbon-14 will be a type of beta minus particle, would release a beta minus particle. A beta positive particle could be something like carbon-11. You can see down here. There's all the various different forms that it can be written in. Please make sure you keep those in mind. And yes, you need to be familiar with both beta negative and beta positive. Alright, gamma radiation. Gamma radiation is probably the easiest one. It is a type of energy. It doesn't release any particular particles other than a photon. And photon, obviously, we link it to light. We say light is light releases photons, so really it's releasing light. Now, it doesn't change the structure, but it does stabilize it in terms of the amount of energy. So one of the ones that we had at school for display, which unfortunately doesn't really work anymore, is bismuth, and bismuth releases gamma radiation. Now, quite often these gamma radiations are released with other radiations. So for example, the one down here, you have a beta minus being released, and you also have a gamma being released at the same time. That is not to say that energy is really a gamma particle, but quite often they're released together. Okay, so just to give you some examples, americium-241 decays by alpha emission. So if you look on the periodic table, americium has an atomic number of 95, the symbol is Am, and it tells you that the mass is 241. So we have an alpha particle, and we said the alpha particle has a mass of 4 and an atomic number of 2. Now because we're going to lose 2 here, if you have a look, 95, we're going to lose 2 here. This becomes 93 on our atomic number. And then if you look on the top, you have 241, and then we're going to lose 4. Because we're going to lose 4, 241 minus 4 becomes 237. Because of that, we can look at our periodic table. Remember, you only look for the atomic number. Do not look at the mass. The mass is going to be different because it's an isotope. Once you look at the atomic number, you should find that that's neptunium. And then at the end of each nuclear equation, do not forget to write down plus energy. Alright, determine the type of particle released for the following. You have lead, 20982, and it goes to bismuth. Now, what you need to do in order for you to determine the type of particle released is to determine which of the particles suit. So obviously we have alpha, beta minus, beta plus, and then gamma. With a gamma particle, notice that there is no plus or minus, or if you like I can put a 0, 0. It does not change the structure. If you have a look on this, it went from lead to bismuth, so the structure is changed. Therefore, it can't be gamma. And then if you have a look at alpha, 82 to 83, that has a difference of 1, not 2, so it also can't be alpha. And because it can't be alpha, it can't be gamma, it's going to be one of the betas. Now, the way you check which one it is you balance the equations out. So 209 in terms of mass, going to 209 doesn't change. So that's fine. We have 82, and that's 83 plus something. Well, 83 minus 1 gives us 82. So this something must be a minus 1. And which one has a minus 1? It's the beta particle, the beta minus particle. So in this case it's going to be beta minus. Now, this graph shows you how many of the elements have stable nuclei. So you see that line of stability. Everything along that line will be stable. Do note how many other particles there are that aren't stable. So the last section here is about Geiger counters. It's just how we detect radioactivity. Now, on the bottom there's actually a YouTube link. I would really highly recommend you watch that. I'll put a link in the description if you're watching it off YouTube. Really good video showing you how radiation, how much radiation there is around the world. And I've been showing it for years. It's a really great video. Go through and watch it.